Okay, 5.3, that section, and this is February the 2nd, and we're going to go through the preview activity to start with here. So we're dealing with the chain rule here. And if you've got function with another function inside it, then it's the derivative of the bigger picture times the derivative of the inside. Derivative of the big picture with the same stuff inside times the derivative of the inside. Okay, so if we were to take derivatives here, just to remind ourselves, of 3 to the x, the derivative of e to the something is e to that same something times the derivative of the inside, and derivative of 3x is a 3. Now this derivative of the inside is what you want to kind of focus on here for what we're talking about here. Okay, so if that's h, h prime of x is going to be, see, the derivative of sine of something is cosine of something, times the derivative of the inside, which is times 5. So focus on that. Arctangent. The arctangent is one derivative of arctangents, 1 over 1 plus x squared, or x squared plus 1, whatever. But the x is not 1, it's 2x, so it's 1 over 1 plus 2x quantity squared times the derivative of the inside, which is times a 2. Again, that's the extra, so we're going to watch that. If we have something to the fourth, the derivative is 4 times that something to the third times the derivative of the inside, which is -7. So that's something I want you to watch. And so on this one here, if we got 3 to the something, the derivative is 3 to the something, derivative is 3 to the same something times the derivative of the base, or times the ln of the base. And times the derivative of the inside, which is -11. So this one has a couple of things showed up here. So now if we try to do the general antiderivative of x e to the 3x, the antiderivative will be, well, since the derivative of e to the 3x is 3e to the 3x times a 3, the antiderivative is going to be e to the 3x, but then we don't want to do times a 3, so we have to divide out the 3. So that when we took the derivative of it, that 3 wouldn't show up. But we're doing general derivative plus c. So when we do this one, the antiderivative of this would be, well, what do we take the derivative to get cosine? We take the derivative of sine to get cosine, so it's the sine of 5x plus 1, so that if we took the derivative, we get the cosine of it times this inside, but we don't want that inside, and the derivative of the inside is 5, so we'd have to do 1/5 to get rid of that 5 that we had up here. We'd have to do the 1/5. On this one, this is 2x quantity squared, so this looks like the arctangent. So the antiderivative, antiderivative of this, the capital S, would be arctangent, or tangent inverse of 2x. That's what creates that 2x, but the derivative of the inside would create a 2, like it did here, times 2, so we have to divide that out, divided by 2. And on this one, something to the third, the antiderivative would be 1/4 that something to the 4th. But then we'd have to divide out the derivative of the inside, which is that creates -7, so we have to get rid of that. And that power thing, we got the 4, so we have to add 1/4. We have to get rid of that -7, so we have to go -1/7 times 1/4. So it's -1/28 that to the 4th. Oh, I kept forgetting here. Plus C, plus C, plus C. And now finally the last one, W, antiderivative. Well, the antiderivative of 3 to the something, the derivative creates an ln3. So the antiderivative, if we don't have an ln3, we have to divide out the ln3 that this would create. So we have to divide out the ln3 and the -11 that would show up. Then we can do 3 to the 4 minus 11x. So the derivative of this created a ln3, so we divide it out. Created a -11, so we divide it out. Plus C. So if we had to do these where we haven't done them before, the derivative of the inside would create a 1/pi, so we'd have to do 1/pi. The derivative inside would create a pi, so we have to undo it, and the antiderivative of cosine would be sine of pi x plus c. This one would create a 4 from the derivative inside, so we'd have to go 1/4 this to, we'd increase the power to 12, so we'd have to also have a 1/12 of this to the 12th. And this one, see, the derivative of x squared would be a 2x. Well, there's an x, but it wouldn't have the 2. So we'd have c of x equals 1/2 e to the x squared plus c. Now the derivative of this would be e to the x squared times the derivative of that, which is 2x. The 2 would cancel, but the x would remain. So that's the antiderivative of that. So that was the preview activity. Now, we could have done those a little differently too, and that's what this section is also about. It's called the U Substitution method. So let's say we had this one, and we were trying to find the antiderivative of e to the 3x dx. This is another way to say find the antiderivative. An indefinite integral. Indefinite means we don't have limits on it. So we're just finding the antiderivative. Now, the part that makes this a little complicated is it's not just e to the x, it's e to the 3x. So we're going to let u equal the complicating piece. I'm making up the variable u, which is just 3x. I'm going to take the derivative of this. So the derivative of u would be du dx, or u prime, and the derivative of 3x would be just 3. But instead of writing the dx down here, I'm going to write it over here. Multiply both sides by dx. So I'm going to say the derivative of u is du, and the derivative of 3x is 3 times dx. That's kind of an easier way to get to this. It saves a step. And then I'm going to solve for dx, which is going to be du divided by 3. Okay, so this integral would become, not this, but the integral of e to u, and dx would become du over 3. Over 3 is like times 1/3, so I can take it out the 1/3, so it's just be 1/3 antiderivative, please, of e to the u du. Now that's one that's pretty easy. E to the u du is just e to the u, but times 1/3 plus c, but I made up the u, so let's get rid of it by going back to 3x. So we get 1/3 e to the 3x plus c. And that's what we had here. So we get the same answer. So if we don't happen to see that it's going to create that extra 3 that we have to divide out, you can do this U sub, and it'll take care of that for us. It'll put in whatever we need to add. Okay? So that's the idea of U sub. Let's do another one. Let's do this more complicated one. This one here, which says, please find for us the antiderivative of x e to the x squared dx. Now, when we're doing U sub, we've got to get used to figuring out what we're really looking for. So what's making this one complicated is the x in front and the x squared. Now, this is what I want you to watch. If I let u equal the x squared and take the derivative, this would be du, and the derivative of x squared is 2x dx. Solving for dx, I get du over 2x. And so that's what I'm going to put in for the dx. And let's take a look at the rest of this here. So I've got the integral. I didn't have anything for x, so I'm going to leave that there for temporarily. Then I have e to the u, because that's what I made u. And for dx, I've got du over 2x. And because there's an x in the derivative, it shows up here, and it'll cancel that x. And now I have a pretty simple integral to do. I've got 1 over 2, which is a half, which I can pull out of the integral, out of the antiderivative. And so I've just got the antiderivative of e to the u du, simple one. It's 1/2 e to the u plus c. And now we go back and put x squared back in for our u, and we get 1/2 e to the x squared plus c. And that's what we decided it was. A little bit more work, but it doesn't require me to have as much insight to how this is going to work. Okay? So, activity 532 says, let's practice this a little bit. So what's the antiderivative of this? Well, what's making this complicated is the 8 minus 3x. So if we use the U sub, we would go u equals 8 minus 3x. du would be minus 3 times dx, because the derivative of 8 is 0. So dx would be du divided by -3. So this antiderivative, this indefinite integral, would become the integral of sine of u times du over negative 3. That would come out as a negative 1/3, so we're going to get negative 1/3. The antiderivative of sine is negative cosine. So the negative and negative makes plus. So this will equal plus 1/3 cosine of u plus c. Okay? Hopefully you see how that works. Let's do this one, b. What's making this complicated is the 4x. How do we handle that? Will it be just a 1/4? And I think it will, but let's just kind of check it out. So if we let u equal the 4x, du is 4 dx, and dx is du over 4. And the integral would become the integral of secant squared u dx becomes du over 4. So that's 1/4. Yeah, like we said it would probably be. The antiderivative of secant squared is just tangent u, because the derivative of tangent is secant squared. And then we got plus c. And we go back and put the 4x in for the u. C. There's always a question about what should we let u be. In this one, should we let it be the whole thing, or just the 11x, or the 11x minus 9? Well, if we do just 11x, there'd still be a minus 9, and the subtraction in the denominator is tougher to deal with. A subtraction in the numerator, we can split the fractions up, but in the denominator, it's messier. So I'm going to suggest that we let u be the denominator, not the whole thing, but just the denominator, the whole denominator. So I'm going to let u equal 11x minus 9. And so du is going to be 11 dx, and so we're going to get 1/11. dx is du over 11, so we're going to get that. But what's going to be left? Well, we'll have the integral of 1 over u du over 11. The 11 comes out, and we have the integral of 1 over u. And the integral of 1 over u, this is one that stumps students a lot. It's that special case. It's ln of absolute value of u. The derivative of absolute value of ln is 1 over. Plus c, and so we get 1 over 11. So we get the derivative of the inside. There's that constant 11. So we divide the constant out. ln of 11x plus c. D, the way it is, it might be kind of hard to recognize, but we see a 2x plus 1 and a 2x plus 1. If we let u equal 2x plus 1, the derivative would create a 2 dx, which becomes a half. And so that integral becomes cosecant u cotangent u. Now that might look a little bit more familiar to you. du over 2. The half comes out. Cosecant of u cotangent, well, if that was a negative, it'd be the derivative of cosecant. So it's negative cosecant u. And then replacing the u, we get negative 1/2 cosecant of 2x plus 1 plus c. So we get that 2 creates a 2 outside, derivative on the inside would cancel out, and the derivative of cosecant is negative, so the negative would get canceled out and make cosecant cotangent of 2x plus 1. Okay, this one. Now the temptation here would be to let u be 1 minus 16x squared. But 1 over 1 minus something squared looks like an arc derivative. So I'm going to let the 16x squared, I'm going to let u not be 16x squared, but I'm going to let it be, I'm thinking of this as 4x quantity squared, so I'm going to let u be the 4x. So if I let, keep it on your screen there, if I let u equal 4x, du would equal 4dx, so dx equals du over 4. So I'm creating a 1/4, and I have the integral, the antiderivative of 1 over the square root of 1 minus u squared, du over 4, and that is the negative of arc cosine, or the arc sine of u, and we get a 1/4 from here, and plus c, so it's 1/4 arc sine of, and that u was 4x. Okay, I want to do the last one, this one. So I'm going to go up here. I'm going to let u equal negative x. du equals negative 1 dx. So dx is du divided by negative 1, which is the same as multiplying by negative 1. So then I have the integral of 5 to the u du over minus 1, or minus it. And so the integral of 5 to the u would be, you've got the minus, would be 5 to the u, but it's going to create a ln of 5, so I have to divide that out. Divide by ln of 5 plus c, which becomes minus 1 over ln 5 to the negative x plus c. Okay, so looking back, this creates a negative 1/3. And the antiderivative of sine made it negative, and so that's why it became positive 1/3. Then the antiderivative of sine, which is this. This creates a 1/4. Antiderivative of secant squared is tangent. This creates a 11. So we get a 1/11 ln, because that would be 1 over u, so it would be ln of that, plus c. This one creates a 2, so we get a half. The antiderivative of cosecant cotangent is cosecant, and it's negative, so that becomes a negative half. This 4x, the 16x squared, which is 4x, creates a 1/4 arc sine. So we're creating this constant, so we are dividing by that constant, negative 1, negative 1. Okay, so they have a rule that says, okay, when you have something like these, you have, if you got the antiderivative of some function with a times x in it, it could be plus c or some other constant inside, dx, it's going to be the antiderivative of ax plus c, whatever that was inside, times 1 over a plus some constant added on. So that's the difference. So maybe I should make this a b. Something that was added on kind of stays in there. That's a rule that they have in there in the book on antiderivatives with a constant times x, a linear thing, a function of a linear expression. Okay, but this one isn't a linear expression. However, if I look at this thing inside, I see that the derivative of this, that's going to go away when you take derivative, but this is going to create 4x. It's going to create x to the third times the 4 and the 7. So again, we're going to do this U substitution. We're going to let U be that complicated stuff, and so I'm going to let U equal 7x to the 4th plus 3. Now, knowing that it's going to create an x to the third and seeing that there's an x to the third, I'm hoping there's some cancellation that'll happen. That's what you got to start looking for. Will there be some cancellation to get rid of something? So the derivative, du, would equal 4 times 7, 28 x to the third. Derivative of 3 is gone, dx. So dx will be replaced by du over 28x to the third. And that's going to be in the denominator, which will cancel something in the numerator. I'm thinking, yes, this is going to work. So the antiderivative is, we haven't canceled the x to the third yet, so I'm going to write it in. Sine, this is what I called u, and dx becomes du over 28x to the third. And the x to the thirds cancel. I just get a 1 over 28, which comes out, and I get 1 over 28. Antiderivative of sine is negative cosine u plus c, but going back to what u was, I let it be 7x to the 4th plus 3, so this becomes 1 over 28 negative cosine of 7x to the 4th plus 3 plus a c. So now, find two functions within the integrand. Well, I see this one and this one. Make a substitution and convert the integral to involving one u with u, and hopefully we'll let u be something where the other one is has the derivative in it. Well, the derivative, this would be x. That does have it in it, but sums in the denominator again are messy. So I think I'm going to let u be what's in the denominator. 5x to the third plus 1 du is going to create an x squared. It's going to make 15x squared. So if I divide by the 15x squared, I get du over 15x squared. And that x squared is going to be in the denominator. That one's in the numerator, and I'm thinking this is going to work. So we'll have the antiderivative, the indefinite integral of x squared, we didn't do anything about it, over u, and du, dx becomes du over 15x squared. The x squareds cancel. I get 1/15 because it's 15 in the denominator. 1/15. The antiderivative of 1 over u is ln, absolute value u. So this becomes 1/15 ln, absolute value of 5x to the third plus 1 plus c. Now, if I wanted to check this, I would take the derivative of this. The derivative of ln of something, I'd have 1/15. Derivative of ln of something is 1 over the something times the derivative of the inside, which is 15x squared, and the derivative of c is gone. The 15's cancel, and I get x squared over 5x to the third plus 1. It matches, so it worked. Okay, this one. So we have the integral of the e to the x sine e to the x. Ooh, okay. I have no idea what that would look like as a function or wherever would be generated, but it's a sine of something. So I'm going to I could let u be e to the x. I could let u be sine of e to the x. I'm not sure which to do. I'm just going to go simple here and let u be e to the x. Well, that's always going to produce an e to the x in the denominator of du, because derivative of e to the x is e to the x times dx. So if I solve for dx, it's going to be du over e to the x, which is going to cancel that e to the x when I go integral. Now I could call that u. That is what u is, so I'm going to get du over u, and that's going to be u. It's still going to cancel, so I can either leave it e to the x or call it u, sine u, and du over e to the x, which is a u, or I can call it e to the x. Those are both u's or e to the x's. They both cancel. And I get the integral of sine, and that's going to be negative cosine of u, because the derivative of sine is cosine, the antiderivative of sine is negative cosine, plus c. So that is negative cosine of e to the x plus c. And finally, the next one. Okay, so I could let u be cosine of square root of x. I could let u be square root of x. Letting it be x wouldn't do anything. I'm hoping the square root will cancel out somehow. So I'm going to let u be the square root. Now the square root is one that most of these have been producing something in the denominator will cancel something in the numerator. Watch what happens when we let u be the square root of x, which is x to the 1/2. So du is 1/2 x to the minus 1/2. And the minus 1/2 means it's in the denominator, so this is 1 over 2 square root of x dx. So now when I solve for dx, that 1 over 2 square root of x becomes 2 square root of x times du. So it ends up in the numerator. So the square root one, if you let u be a square root, because it's a half and goes to negative half, it ends up in the denominator. So when you solve for it, it ends up in the numerator, and so it'll cancel stuff in the denominator, which I like on this one. So this becomes the integral, the antiderivative of cosine of u over the square root of x, which is also u, but then I have du, not over, but times 2 square root of x, and the square root of x is canceled. This 2 is in the numerator, so it becomes 2. Antiderivative of cosine is sine. So my answer is going to be 2 sine u is the square root of x plus c. Let's check it by taking the derivative. The derivative of a constant's gone. The 2 would stick around. The derivative of sine is cosine times the derivative of the inside. Derivative of x to the 1/2 is 1/2 x to the minus 1/2 times 1/2 x to the minus 1/2. Minus 1/2 means square root of x in the denominator, which is what we were hoping to get. And the 2 cancels the half, and so we get cosine of square root of x over a square root of x. So it checks out. So now, what do we do when we have a limits, a definite integral? Okay, so in this one, we've done this one already, and we would have let u equal x squared. So du would equal 2x dx, so we get du over 2x is dx. So this would become, and here's where it gets a little different. It would be still the antiderivative, but it's between 2 and 5 for the variable x. But what will it be if we're doing u? If our variable's u, when x is 2, u would be 2 squared, which is 4. And 5 for x, u would be 25. So this, if we're changing to a new variable, the limits change. And then we'd have x and e to the u du over the 2x, x is canceling. So now we're in variables of u, and we're going 4 to 25, which would be integral, the antiderivative of e to the u is e to the u, and we have this half that would come out, and we'd have to evaluate that from 4 to 25. And if we put 25 in there, we get 1/2 times both of these. So I'm just going to go 1/2 e to the 25 minus e to the 4. Or I could change the u back to the x squared. And so then it would change this to 1/2 e to the x squared. Now I'm back in the x's. I would change my limits back from 4 and 25 back to the x limits of 2 and 5. And if I put 5 in here, I get 1/2. It's going to be times both of them, so I'm going to write 1/2 parenthesis. 5 in here is going to be e to the 25 minus e to the 2 squared, which is 4. Notice I get the same answer whether I change my limits to the u limits and finish her off that way, or change it to the u and then change back to the x and go back to my x limits and work it out. So sometimes I don't even do these. I just leave a question mark here, knowing that I want to change back to the x limits. I'll do this, go back to my x limits, and then finish the problem. Okay? So that's what they're trying to show you here. They go 2 to 5 on this. They change to 4 and 25 when we go to e to the u, and then we solve it that way. Or we get to this, and we keep the x limits if we don't use u, but go back to the x squared, and we get the same answer. So here's a few to practice on. Now, here's one that you might be tending to say, okay, this is look like 1 plus x squared if u was 2x. But if we let u be the whole thing, the derivative is going to produce an x, an 8x. And that will show up in a denominator, which will cancel the x. So I'm going to let u be, I'm going to come up here, no, I'll do it down here. I'm going to let u be 1 plus 4x squared. Even though this looks like it might be an arctangent, it isn't. So du equals 8x dx, and dx is du over 8x. That x is going to cancel that one. So this is going to become the definite integral. When I go to u, it's not going to be 1 to 2. It's going to be 1 squared, 1 times 4 is 4 plus 1, 5, to 2 squared is 4 times 4 is 16 plus 1 is 17 of x, which I know is going to cancel, that's why I'm not worried about it, over u du over 8x. The x's are gone, so now I'm okay. Everything's in u. The limits are in u, so I can go to, see, the antiderivative of 1 over u is ln absolute value of u plus c, but I'm doing a definite integral, evaluated from 5 to 17, which is going to be ln, I can drop the absolute value because 17 is positive, minus ln, and that's positive. And if you want, subtraction of logs, if you remember your log rules, is ln of 17 fifths. We have ln of a log of a number minus log of a number, that becomes the log of this division problem. Now, let's say I decided to go back to x's here. Well, then this would have been ln of, not u, but 1 plus 4x squared. And now I would be going back to the old limits of 1 and 2. And you'll notice I'll get the same thing, because when I put 2 in here, I'll get 4 times 4 is 16, plus 1 is 17. I'm going to get ln 17, minus, and I put 1 in there, I'm going to get ln 5, and I'm back to the same answer. So you can change the limits and continue on and stay in u, or you can change back to x's and use the limits, the original limits. Okay, b. Well, look at this stuff to the 9th. However, the derivative of 3 is going to be gone. Derivative of e to the negative x is going to produce an e to the negative x, which will probably go in the denominator and cancel that. So I'm going to let u be this messy stuff. So u is going, we're going to let it be 2e to the minus x plus 3. Du would then equal 2 is a constant. E to the negative x will be e to the negative x times the derivative of that, which is negative 1. And the derivative of 3 is 0, so we get that dx. So we're going to get dx equals du divided by negative 2 e to the negative x. So our new limits are going to be, if I put 0 in, e to the 0 is 1, times 2 is 2, plus 3 is 5. If I put in 1, I get e to the minus 1 is 1 over e. So I get 2 over e plus 3. Not very pretty limits. So this is one where we might excuse me, want to just go back to x and go use the 0 and 1 limits. But we're going to have e to the minus x, u to the 9th, and du over negative 2e to the negative x. And there goes the e to the negative x. X's are gone. So we get the integral of u to the 9th is 1/10 u to the 10. And then we have a minus 2 in the denominator, so it's minus 1/2 plus c, or definite integral. Excuse me. We don't have to have it, so it would go from 5 to this 2 over e plus 3, or changing back to x, see that'd be minus 1/20 of 2e to the minus x plus 3 to the 10th, from 0 to 1, the original limits. So I could have put this in for you, so it had this to the 10th minus 5 to the 10th, both of them times negative 1/20, which is what I'm going to get from here. I'm going to get negative 1/20 2e to the minus 1, which is over e plus 3 to the 10th minus, put in 0, e to the 0 is 1, times 2 is 2, plus 3 is 5. And same thing I would have gotten if I had to put this in for there, and 5 into there, times the negative 1/20. Okay, I hope you can see where this is all going. Okay. Now we got a denominator, x squared. Do we want u to be that, or do we want it to be 1 over x? So it's a little bit of getting used to these, that you'll realize that 1 over x is going to, the derivative is going to cancel that x squared. Watch how this works. So if I let u equal 1 over x, which is x to the minus 1, now I'm not taking the integral, which would, the antiderivative of 1 over x is ln, but I'm taking the derivative, and so it's going to go the other direction. So it's going to be du equals minus 1 x to the minus 2, which is minus 1 over x squared dx. So this time the x ends in the denominator, and so when I put it, solve for the dx, it's going to end up in the numerator, minus x squared du. And that's going to cancel that x squared there. So I'm going to have the integral of, let's see, going to u, so pi, 4 over pi, the antiderivative of, let's see, I'm going to figure out what u is. So that's 1 over 4 over pi, which would be pi over 4, because u is just the reciprocal of x. So that's going to turn that over, and that's going to turn this one over to pi over 2. And the antiderivative of, it's going to be cosine of u over x squared. That's this part. And then the dx becomes negative x squared du. X squareds cancel, the negative doesn't, so I get negative. Antiderivative of cosine is sine of u with my new limits, pi over 4, pi over 2, pi over 2 to pi over 4. Whoa. That's actually going backwards, so it should give me a negative number because pi over 2 is bigger than pi over 4. So I could switch those and make this plus, but in fact, I think I will. That'll be switching the limits of this. It'll be change the sign on this. Will be sine of pi over 2 minus sine pi over 4, or if I hadn't, it would have been minus sine of pi over 4, which is that, minus a minus, which would be plus sine of pi over 2. And if we remember our trig, the sine of pi over 2 is 1, and the sine of pi over 4 is square root of 2 over 2, and I'll leave it there as the exact answer. Or I could have switched back and it would have been minus sine of 1 over x evaluated from the original limits 2 over pi to 4 over pi. Now that's bigger than that in this form, and so we would get minus sine of the reciprocal of that, which is pi over 4, minus a minus, which is plus the sine of the reciprocal of that, which is pi over 2, and we'd get minus square root of 2 over 2 plus 1. Hopefully you're starting to get a feel for how this u sub and the derivative of whatever we use for u is used to cancel stuff. It canceled the x in this. If we let it be 2x, it canceled that. Or the whole thing here, 4x squared, creates an 8x, and the x canceled. In this one, it created an e to the negative x, which canceled the e to the negative x. And in this one, 1 over x creates an x squared in the numerator, which canceled. So that's kind of what we're kind of watching for when we're doing u sub, is those ways that it cancels. Okay, and that's going to do it for presentation.